So today we have Alessandro Gianola telling us about compositional SMT-based verification of data web processes. Thanks for visiting.
Thank you so much for introducing me. And in my talk today, I'm going to talk to you about my research activity and this research project, which is somehow the sort of collaboration from different universities between Università degli Studi di Milano and the Free University of Bolzano mainly, but now also I'm also visiting at University of California, San Diego. And the idea is trying to combine two different approaches, two different traditions. So the first one, let's say, it's more categorical oriented, so it's about compositional control flows, how to formalize compositional control flows using a model which is called span graph. And the other tradition, the other approach is about the verification of data-aware processes, so processes that can be enriched with data, and using some SMT techniques, so satisfiability modulo theories techniques. So a lot of logics, let's say. And as you can see in the picture, the idea is that our automated verifier should balance the data component and the process component in our theory and also in our implementation somehow. So as I was saying, somehow here there are two different traditions and there are many people involved. This is a list of my collaborations. So span graph is due to Robert Walters. Unfortunately, I haven't worked with him because he died before I started to work with Nicoletta, but okay, so that's why I cannot say that he is one of my collaborators, but okay, span graph is due mainly to Nicoletta and Bob, so that's why I have reported it. And also, of course, Nicoletta, Stefano Casangian, Filippo Schiavio, and also others like Simonettini and Desiree Manicardi. And concerning the other part, the verification of data-aware processes approach, let's say, there are other people that work on that, mainly Silvio Ghilardi from Università degli Studi di Milano, and Diego Calvanese, Marco Montali, and Andrea Rirkin from the Free University of Bolzano. So let's start with a very brief outline. First of all, I'm going to describe and tell you about some motivation and some intuitive reason why it's very important to provide a sort of combined model where it's possible to cook, let's say, with data and processes at the same time. And the idea is to have sort of, the final goal is to have a sort of compositional process flow and plus data. Then I will focus on compositional algebra for representing the control flow of processes, which is this model called span graph. And finally, I will just give you some very brief intuition and some detail about how to model and how to verify using SMT-based techniques data-aware BPMN, where BPMN stands for Business Process Model and Notation. This is a standard language that is used in the BPM community, and BPM stands for Business Process Management. Okay, so first of all, let's move on to how to cook with data and processes somehow. So the idea is we have to amalgamate things, we have to cook, that's why we have Gordon Ramsay here. And this is a very challenging research field, let's say, because we have to combine and to integrate different approaches coming from different research fields. And also, this is somehow a must. It's needed to reason about these things if one really wants to understand how very complex systems, processes, work using data and processes at the same time. And also, when you want to verify them, you have to take into account all these combined things, let's say. And also, if you focus on industry, and this is a very difficult problem, since usually the experts from data and from process traditions usually tend to be a bit skeptical about using other things than the things that they use themselves, because somehow the BPM professionals usually think that data are not the main ingredient that should be considered, and vice versa, master data managers do not take into account so much the business process component, let's say. And this is also reflected in most companies where there's no interaction between these two groups usually. Why it is very challenging, and this attempt to combine data and processes, the reason is that the standard language that is used in BPMN, which is a language for describing workflows of processes, doesn't take into account so much the data component, and usually let's say that a proper interaction between the process flow and the data component is not reflected at all, or it is just partially supported and implicitly defined. For example, if you have, as in this case, a travel reimbursement request, and you receive a request, and your company receives a request, you have to deal with this request. Of course, there are some data that are involved, and usually maybe the data could be the travel request, could be an amount of money, and which is a data, and so you need some variables to contain this data, but also maybe you need proper database, let's say, so a persistent storage, maybe like the overall budget that the company has. But somehow all those things are not supported, and even if you want to extract some value, maybe if you want to query the database, if you want to perform some update over the database or over the variables that are involved, this is not supported at all in these languages. And also maybe also in your control flow, it could be possible that if you want to change one path or the other, so if you have a decision point, the decision point should consider somehow a sort of evaluation of the data. And also these conditions, which should be, let's say, maybe SQL condition or first order logic conditions, are not considered in this formalism. So that's why all those things, not just the data component, but also how the data and the process can interact each other, are submerged into this very dark, in this dark ocean with dangerous sharks. So the first challenge that we have when you want to deal with combining processes and data is that your formalism that you're going to use is a compositional formalism, which means that if you have different workflows and you want to combine them into a combined and integrated workflow, you should be able to do that. And that's why the first question that I have here is how to define a formal model where you have composition of business processes. My answer will be this categorical framework called span graph. And here I just want to give you a very small intuitive example, intuitive idea of how can you build a sort of compositional system. This is, for example, the heart system. We have formalized this recently in a paper in Fundamenti Informatici, where you can see that all the components of the heart can be, let's say, put together into, they are automata, all of those things. So let's say they provide a description of the processes, and they can be combined using some operations because we have an algebra that describes this. For example, these operations could be sort of tensor when you just compose things in parallel without any communication between among the automata, but it could be also a composition with communication. So somehow you have to identify some states here and some states here using this operation in the algebra. The other challenge is, okay, this is for dealing with the composition of workflows, but there's also the other problem. The other problem is how to integrate BPMN, so the business process part, with data. So somehow we have our process schema, we have a data schema, but we should also take into account this data manipulation logic, because the data schema should be queried by the process schema, but then the process schema should modify through updates the data schema. So let's say that the final goal that we want to reach is to perform verification, so somehow detecting bugs, and this is a very rough definition of formal verification, the automated analysis of a formal model against some properties of interest, considering all the possible behaviors of the system. And so let's say the problem is that we want to perform this verification in a combined framework where all the ingredients are all together, let's say. So we should have a compositional, we should have compositional control flows for processes, we should have a data component, the possibility for querying and updating the data component, and our verification logic and our verification language, but also the techniques that are involved that should take into account all those aspects at the same time. What is the solution? Well, there could be many solutions for this problem. Maybe one can introduce some new formal combined verifiable model, but there are many candidates for this. For example, Petri nets, or some automata-based formalism, or maybe a declarative SMT setting, which is the one that we employ, or even other formalisms that are more, let's say, practice-oriented, so that could be more understandable by a more applied community, let's say. I will argue in my talk that this is, in our opinion, for the moment, the best solution, since we can make use of SMT solvers, which are very efficient, and are super performing, let's say. So if you have to handle very complicated problems with many variables, with many things, maybe this setting could be, in my opinion, the best one. And also consider this a full declarative setting, so you have just to express all your requirements, all your properties, all your systems using first-order formulas. First-order formula. So let's now talk a bit about our categorical approach for workflows, and this is called span graph. And okay, so the definitions are quite standard, I think. So a span graph somehow is a category where the objects are graphs and the arrows are spans of graphs. So this is the arrows. This is an arrow between A and B. And the very nice thing here is that we have a sort of semantics. We have an interpretation for this, because if you consider that, if you think of X as a sort of automa, in this case it will be because our X is a graph, is a label graph, then the legs, let's say, of the span are somehow the interfaces, so something that can be used to be connected with other span. Okay? Yeah.
Where would C and D up there?
I think it's X from.
No, it's another thing. I mean, it's separate. This is a very simple. This is a very simple example of span. This is a more complicated. Okay, this is a more complicated span. Let's say where X is the automata and the automa and the interfaces are here are A times B and the other interfaces is C times D. So, okay, let's say that A here, there, here it's A times B, okay, and the B there, here is C, okay. You see, because this is the left interface, this is the right interface, this is the left interface, this is the right interface, okay. And I was saying that somehow the idea is that you have a sort of automa here, and you have the interfaces that can be used to build sort of open network. Okay, so you have an automa, but this graph is not isolated, but it can be connected with other graphs using the interfaces. And of course, this algebra provides some operations. For example, we have the parallel composition, and the composition of arrows is done by pullback. So here the idea is that, so how use, okay. So the idea here is that you have two spans here, this one and this one, and they have in common one interface. So the idea is that you can combine these two graphs, these two spans, building the pullback, and the combined states here somehow will be synchronized over this B. Because if you have, let's just give a very easy, I mean, if I have X here, Y here, A, B, and C, and if I build my pullback, so if you can imagine that here you have the Cartesian product, let's say, of course here you will have X, here you will have Y, which are vertices in your graphs, let's say. That means that somehow the Fx should be equal to the Gy. So these states are synchronized using this common interface. Is it? Are you still with me? Yep. Okay, perfect. And okay, we have a way for representing this using geometric representation, let's say. And of course, here our B is a C and D, as before. And this is the semantics, this is the interpretation. We have a parallel composition, and we have a sort of communication done through this B. So in this case, synchronization happens in C times D. And yes.
So X and Y are states. So capital X and capital Y are graphs. And then little x and little y.
No, that's element in a graph.
Right, little x and little y are vertices.
Vertices, yes.
Okay, but the arrows are transitions, right? So what do you mean? What does it mean for states to be synchronized?
Yeah, in this case, it means that of course you will have. Usually this B. Okay, let me give you an example. Usually you will have a sort of, okay, you have vertices, you have arrows of graphs, and that means that, for example, this is x1, this is x2, and in y you will have y1 and y2, and here you have another arrows. That means that these two arrows are mapped in the same thing, because this F. Usually B, it is just a singleton. So think as all the arrows that are mapped in a loop.
So it's the arrows that are synchronized.
Yep. Because the point is that, are the arrows that are synchronized, but also all the vertices, because all the vertices are collapsed to a single vertex. Right. Okay? So the idea is that, yes, for vertices, it is for granted, let's say, because here usually you just take the singleton, but the real feature here is that you synchronize the arrows, of course. And here in the other case, in the case of the parallel composition, without communication, you somehow exploit the the symmetric monoidal structure of this span graph, and you have tensors, and the idea is that you just superpose the two automata. And of course it is a symmetric monoidal category, so this is not surprising. And in the parallel composition, without communication, you just have the two automata that work independently. This is a very nice example, so here maybe it's clearer what we have. So here we have a decimal counter, and the idea is that consider is as a span, this is another span, this is another span. This is the head of the span, and these are the interfaces, okay? These are the interfaces, and so on. So let's say that let's call one component x, which is the graph. So x is this, okay? And we have the interfaces, so just singleton here. And the idea is that okay, we have a loop.
Just one loop in the terminal graph?
Yep. Yeah, it's the terminal. It's the terminal. It's the terminal. No. This is notation for denoting the arrows. So in this case, this notation, epsilon s, okay, means that through the right interface, you have to, it is sent to s, okay, and in this case it is sent to y, to epsilon, okay, okay. So you were asking if this is a terminal. No, this is not a terminal because you have more loops. So you have one loop for every edge, okay? So the idea here is that when you pass from a state S to a state 1, the effect that you have on the right side is that you have the S effect, which means that if you have another component here, you pass through one state to the other. While if you have the epsilon, you do not do anything. So this is exactly the semantics of the decimal counter, because here when the units are going on, in the other side you don't have anything because they are the tens until you reach the 9. In this case you have, okay? So as you can see, the main feature here is that the model is compositional in the sense that the semantics of the combined model can be obtained it can be deduced just considering the semantics of its constituents. And of course we can build circuits in span graph. We have, of course, we have other features in span graph. We have units, co-units, and we can exploit these in order to construct more sophisticated example like sort of parallel feedback in this case. And the nice thing is that for every geometric representation, we have an algebraic expression. So in this case, for example, epsilon, the unit will be, well, if I remember correctly, the span is, you have x. So here you have the delta, and here you have the terminal. That's why it is represented like this. And here you don't have nothing because you have the terminal. Okay. Of course, we can consider the dual category of span graph, which is co-span graph, so just reversing the arrows. And the idea is that it seems very similar, but from the semantical point of view, it's not, because the automa X, now of course the head is always, okay, maybe now it's weird to call it the head, okay? But the point is that this automa is still, let's say, an automa, a graph, but the interfaces are not considered interfaces anymore, but are considered as conditions. So somehow this is the initial condition, and this is the final condition. Because through F and G, through F, for example, this initial condition can identify some, can select some states here, and they are considered as the initial condition. And here, in parallel, you have the same thing. You have some states that can be selected as the final conditions. And of course, you have the dual operation. So the push out is the composition of arrows, and the interpretation of this is a sort of sequential composition, because you are identifying, you are gluing your automata through the final condition of X with the initial condition of Y. So somehow the execution, the control of the execution before was by X, and then you have it in Y. So somehow we are changing the topology of our nets, of our system. And that's why this is a sort of sequential composition. Before we have X, then we reach the final conditions. So, but these are identified as the initial condition of Y, and so the idea is the same as in span graph for the pullback. And of course, you can define the combined model. So you have cospan, span graph, a combined compositional algebra. And the span component is used for the composition, the parallel composition, and the cospan component is used for the sequential composition. So somehow the idea is that you start from this. For example, this is the example of a distributed sort. So you have an atomic sort here that receives a stream of items, but at a certain point maybe since this is bounded, you have a bounded size, maybe cannot finish. So the network is changed. So before you have a divert here. So since this is not enough, the point is that some items are sent here, other items are sent there. So they work in parallel. So here we have a parallel composition, and here we have a parallel composition with communication, because there's communication between these and these. But here we have a sort of a tensor, so a parallel composition without communication, because they are independent, and then they are merged. So this is the merge. Here you are divert and the merge. But maybe two atomic sort are not enough, so you change again the topology of your net, and so on. Of course, these are cospan operation, because before you have this, then you have this, and finally you have this, and maybe you can go on. So the nice feature of this cospan span graph model is that it represents an open and reconfigurable network of automata.
Are you going to say the formal definition? Or?
Here?
Yeah.
No. I don't. I'm not going to give you the formal definition. Okay, right.
I'll ask you after.
Okay, yes, okay. No, it's not that difficult, but I mean, it's a bit involved, and I have many things I want to say. So I think that in Sabadini at 2017 you can find this. I'm not sure. In Calco, in our Calco, in our Fundamenti Informatici, there's not there. So, okay. Now, somehow, since the idea was to give you a very brief idea of how to provide a sort of compositional framework for workflows, I want to spend the second part of my talk just to give you a sort of intuitive idea of the data component, because the final goal will be to combine all those things into the same framework and to perform, in order to perform verification. Because in this setting, for the moment, we just have a model. We have, I mean, I've just said things about the modeling part and nothing about the verification part of this, of course. And the point is that also another thing that is missing right now from the modeling point of view, so how to incorporate data. And let's say that our starting point here is from this formal verification tradition in satisfiability modulo theories. And the idea is to use this framework, this abstract framework, which provides SMT techniques for verification, and this formal framework is called the array-based systems, in order to define a formal model for treating with data-aware processes. This formal model will be called the relational artifact systems. But this is a very abstract and mathematical model, and since we also want to do something that is useful in practice, we will translate this model into a more practice-oriented model. This model is called DEB. And the idea, this is a future work, trying to incorporate span graph for the compositional part of the workflows. So if you, the point is that you should also consider the data component. So maybe you cannot just take span graph as it is. So, okay, just 2 words about the SMT. This model is called array-based systems. Does this work on this paper on logical methods computer science. And the very important thing of this model, that's why we use this, is that we can use SMT techniques, we can exploit SMT techniques in this model for performing verification tasks. There are many advantages for using an SMT-based approach, because it's a declarative framework. We can use decision procedures for several theories. It's very expressive, it's very flexible. We can integrate all the new techniques that are used in verification formal methods like acceleration, abstraction, invariant synthesis. It's a universal approach that can be applied to a large spectrum of applications. And also we can use, and this is the most important feature, we can use this, we can employ, using this formal approach, the state-of-the-art and the super-performing SMT solvers. So this is just to say something about, in general, SMT array-based systems, but our model, our formal model, our mathematical model for data-aware processes is this. You have a read-only database, you have, which is the static information part of the system. So here the data are static, cannot be changed. You have the artifact part, is called like this because in the literature it's called artifact, working memory. So are variables and relations, so the part of the database that can be evolved over the time. And you have actions, so an abstract way for representing the process component of the system. So you have the data, you have the process, and the data are split into a static part and an evolving part. That's it. And we can formalize this in our abstract mathematical formal model, which is called relational artifact system. Here we use a first-order theory for this. We use some variables and arrays. I don't want to give you the details about this because it's very complicated, but the point is that's why it is called array-based systems, this tradition, because we use arrays for formalizing relations here, and the actions are expressed by using symbolic formulas. So somehow this tau is a formula that says that the current state, xa, is evolved to x prime a prime. So this is the current state, is the next state. So the pros of this approach is that it is an array-based system, so we can use SMT techniques. But it is a very abstract mathematical model that combines data and actions, which is nice because we can prove a lot of theorems using model theory and logic. But let's say the drawback here is that the process component is not explicitly represented because we have these actions, okay, this formula, this tau, but it's not clear it's not user-friendly, let's say, and the point is that we want to use to perform verification that can be understood by people that work in industry, for example. So the process component is not explicitly represented. That's why we had introduced another model, DAB, which is more user-friendly. And the idea of this model is that, of course, if you remember the second challenge that I've said before, we want to integrate the process schema and the data schema, and these two components should be connected using a data manipulation logic layer. And this is an example of our formalism, of our BPMN formalism. So this is the process component, this is the data component, and the manipulation logic can connect them. This is an example of a job hiring process. So you can see that in the process, you have a sort of structures that are very similar to the one that you have in span graph, because you have circuits. You have sequential composition, you have loops, you have so feedback, sort of sequential feedback, but also parallel feedback. Maybe you can have independent processes, so these independent processes are tensors, and so on. So that's just to give you the possible direction of this. And yeah, sorry, I'm not going to give you any definition, very abstract, because I don't have time. I mean, so the point is that the abstract model, these RASes, they can be used for doing SMT verification, can be equivalently expressed as this more practical model. And DABs use this standard BPMN language for the process schema, which is a user-friendly, clear representation of control flows. The process schema, this is just an example. As you can see, the tasks can be thought as automata, for example. So this is a task, this is a task, this is a task. And the control flow is just a composition of automata. And the data manipulation logic, you have sort of kind of ways for expressing the interaction between the database and the process. For example, maybe this is not the right, okay, maybe, okay, this is a very easy query. Maybe it could be the case that there's a task that is querying the database, and he really needs a user, so you have a very easy query that you are just retrieving a user from the database, or maybe you are retrieving a score, and this usually is done to perform also update of the database, because you have a process. This process can evolve the database, of course, so you have preconditions over your queries, then you have updates over your database done by the process schema. For example, this is an example of update. Maybe you are here, you are in this task. This is an example of an application for a job for a job position. So somehow here you have a job position that is created. You receive some applications for this job position, and there's a sort of application evaluation. This is a loop. And at a certain point, all the applications that have been received are evaluated as eligible or not here. And in order to do so, you have to perform a sort of update, because, for example, you decide that the eligibility is if and only if the score is greater than 80. So that means that you have your relation application in your database, in the evolving part of the database. And if this S is greater than 80, then you have to update this application, and it becomes eligible. In the other case, it's not eligible. So once again, the idea is that you have a data layer logic that can interact between the process and the data, and the process can modify using these updates the data component. And this is the model, how to perform verification here. Well, the idea is, since here we have SMT-based techniques, we use the same SMT-based techniques here. Somehow it is the same model, but it's just a reformulation of it. And this verification is done parameterized over the data, which means that is irrespective of all the possible data that you have. So this is independent of all the possible read-only database that you have. For example, that means that you start from an initial condition. Your system can be evolved through transitions, thanks to the process schema. And the question is, it is possible to reach a configuration starting from the initial condition, whatever is the database is. So if you consider all the possible evolution of the system based on the initial database that you have, and if, for example, these are bad states, the idea is that if you prove that it is not possible for all the possible databases that you can have, which are possibly infinite, the system is safe with respect to this property, because it's not the case that you can reach these bad states in every possible case. And how can we perform this verification? The idea is we start from the unsafe configuration. We compute preimages, so states that the set of states that can reach, in this case, the bad states through the process schema through transitions of the systems. And if at a certain, we do it iteratively. If at a certain point we reach a fixed point, so we don't intersect the initial configurations, the system is safe. Otherwise, it could be possible that we intersect the initial configuration. So there's a path here that leads to the bad states, so the system is unsafe. It could be also the case that this preimage computation does not terminate in this case, because this problem in general is undecidable. But we are able to isolate very, very interesting decidable fragments. So, and also in applications, this is not really the case. But of course, this is just an intuitive representation of this backward reachability. This is the name of the algorithm, which is implemented in our model checker that we use, which is an SMT-based model checker. But the question now is why it is SMT-based. So where is the SMT part here? And is the answer, this set theoretic algorithm is implemented using a declarative version of it. So here we have satisfiability modulo theories check. And this is just, I mean, to give you an idea of the algorithm. And these are all satisfiability tests that are there are proof obligations that are discharged to this SMT solver, and that's the idea of the algorithm. And of course, backward reachability can be modified in order to handle also our case. I said modified because the presence of data of the database requires to develop sophisticated quantifier elimination techniques, but I'm not going to talk about this today. We have also some initial experiments, and they are very promising, let's say, because they are all few seconds or even less than a second. And the properties that are verified are properties that are relevant. For example, is it possible to select a bad candidate as a winner in our job hiring process or something like that? And we check these using SMT. So let me just conclude and to give you an idea of how to connect this with the cost-span graph. So this is what we have already done. So this is a sort of foundational and practical route from the SMT tradition to this more abstract model to a more practice-oriented BPMN model. And we have here a very sophisticated theory using logic and model theory. And here we have in implementation, a tool for doing that. But the question now is, how about having compositional depths? So the problem that we now have for the moment is how to have a specification language for the control flows that for our depths that can be combined using some compositional framework, and at the same time having a logic, a corresponding verification language that can take into consideration this compositional aspects. And as I was arguing at the beginning, the idea would be to incorporate our span graph, or maybe even other formalisms for specifying the process layer in a compositional way. The problem will be also to have a logic that is well behaving with this modification. This is also a question for you or for, I don't know. And an idea could be to formalize all the BPMN constructors in span graph. For the sequence flow, you can use span composition. For different independent pools, which means different processes that are independent, the tensor composition. For loops, the sequential feedback. So the structure of circuits that you have here and you have here are very, 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 very similar. But this is, of course, a work in progress. Maybe Petri nets could be, there are some of my co-authors that are working on DB nets, so Petri nets that are extending with data. Maybe this could be a sort of connection between DABs and more abstract model from category theory. And future work, apart from what I have already said, these compositional RAS, compositional DABs, we have other types of verification that we are interested in. We want to benchmark DABs, we want to introduce richer systems with arithmetics, data types, and also in this case we just check safety, so a sort of reachability. But in general we're interested in different types of properties like liveness, fairness. These are relevant publications, and we have all the theory about this can be found in our mathematical structures in computer science paper that is going to appear this year. SMT-based verification of data-aware processes, a model theoretic approach. While the more BPMN thing can be found in our paper in BPM at the BPM conference, formal modeling and SMT-based parameterized verification data-aware BPM. The things about span graph, there are this calco somehow is a survey. We have this very recent Fundamenti Informatici, which is about using span graph for describing for a compositional description of systems like a heart system. And for the original papers, for example, there's the Katis 97. This is the original paper where span graph has been introduced by Katis, Sabadini, and Walters. And also here, this was the first time that they introduced cospan in this 2000 paper. And also there's also this paper about the general model of span and cospan in Sabadin Theoretical Computer Science, 2017. Okay, thank you for your attention.
So I guess span graph is a two-category.
Yep.
So how do I interpret a two-categorical structure
Yep.
in terms of the automata?
Yeah, it is.
Like, right, but like, so like composition and like the monomodal structure corresponds to some, like, you can interpret them in terms of like these, like the automata, like they correspond to like composition, sequential and parallel composition.
I'm not sure to get your. Sorry.
What does the two structure tell you about automata?
Where I don't know in terms of automata. I don't know. In terms of automata, I have no idea.
Just span graph.
I have no idea.
Are they simulations? So that they're a map of one sort of directed label graph into another directed label graph. So under some interpretation,
Could
maybe
be.
if you make them sort of FE in some way, that's the simulations or something like that.
But I don't know. Could be.
So do you make programs like you make actual model checkers that people use, or
Yep.
Or do you
Yep.
These what kind of people use them and for what? I mean, just for this. But,
okay, so MCMT, the model checker that we are using and also that Silvio Ghilardi is developing, has a very long, it's a long-standing model checker. The first time maybe, I think that the first paper was an HCAR paper in 2008, and it has been used by several people for several kinds of applications, fault-tolerant systems, distributed systems, also by people from FBK in Trento, which are one famous SMT verification group in Italy. And also there are also other tools that use the same idea. For example, there's Cubicle, and there are Cubicle was developed by some people in Paris, but it's the same idea of MCMT, and there are some CAV papers. So CAV is the most important conference in formal methods and computer-aided verification. So yes, the idea, of course, is to continue a sort of already existing tradition in verification, and also the SMT solvers that are used are state-of-the-art SMT solvers. So all the things that are developed in this context can be adapted in our, and that's why it's very promising, let's say, using this kind of techniques instead of others, because the problem here is that usually you have to build on top of something that is already existing. Otherwise, you have to implement everything at the beginning, and that's also a big issue. So in our case, we developed a theory for adapting a very sophisticated theory, because all the applications that were before us didn't involve the data component at all. And when introduce the databases, you have to consider the constraints coming from database, from relational model, and so on. And then you see that you need a sort of quantified elimination for deal with this data. Otherwise, the SMT solvers cannot work. And this quantified elimination is something that is very sophisticated. And somehow we solved this problem using sort of uniform interpolation approach, which is we have one paper last year about this at the International Conference on Automated Deduction. So the idea is we are trying to build on top of something that is already existing from the implementation point of view, but we cannot do it without developing a further, more sophisticated theory, and that's what we have done before. Now we are trying to implement, of course, to implement also these additional quantified elimination procedures that are required in our case. But the idea is not just to have an implementation that somehow we have, but also to develop a sort of benchmark this just from the implementation point of view and from the experimental point of view. The theoretical questions that we have are, first of all, that compositional question that I'm trying to introduce to you today, but also other kinds, the kind of theoretical question could be, for example, that here we just do a sort of reachability. So it is possible to reach a state, but we don't know anything about it is possible to reach this state infinitely many times. So this is sort of liveness or other kinds of verification tasks that are beyond safety, beyond reachability. Like LTL, some suitable first order versions of LTL, linear temporal logic.
So you were drawing string diagrams that went both horizontal and vertical.
Mm-hmm.
I'm wondering, does the cospan and span graph, does that form a double category? Is that what's happening there, or is there, or how am I to interpret this diagram?
I don't know. Do you have any suggestions? Do you know that? It's a double category.
So I think
think the construction is just you have like directed graphs labeled in some edges, and then you can take spans in that, and then that's a thing. And I think it's just okay to take cospans in that.
But what are the two cells?
The two cells. Like cospans are spans, right? So you have these like. So you end up drawing these things with 9 objects, 9 graphs, and like all these arrows between them.
Oh, okay.
And so, and you can just, because there's limits and co-limits commute, you can just do that. I don't know what they do.
Yeah.
That's the one I'm slightly confused about right now.
And do you think that it could be useful to see it as a double category? I mean, in terms, because the point here is that whenever you see the kind of structure that you have, you can exploit some structure for some proper operation over it. So for example, here, why is it important to see it as, I don't know, a symmetric monoidal category? Because you have the tensor has proper, clear semantic interpretation that is useful for us. Or why it is important to have, I don't know, some kind of composition operations of pullbacks or of push-outs. So if this vision could be useful,
Double categories have a string diagram calculus
Yep.
that has
Maybe.
both vertical and horizontal flowing
Yep.
lines. So that's really why I asked.
Yeah, well, some kinds, from a certain point of view, we have the possibility of writing circuits and algebraic expression just using the operation that we have and some constants like the unit, the co-unit.
Yes. That's all in one direction. We can extend that.
Yeah, I think that might be about time. So that's, Alessandro once again.
Thank you so much.